So chapter 11 brings us to the world of vectors. We've been working with vectors up until this point, maybe without really realizing it, because vector quantities need to have both a magnitude, right, a size, and a direction. So things like velocity and acceleration are actually vector quantities. We just never really called them vectors. All right, and most of what we have done has been with scalar quantities, things that only need just one number to describe them, like temperature, length, distance, etc., etc. All right, so this one section in chapter 11 is going to give us the vocabulary that we need in order to do some more interesting and calculus-y things with vectors. So when you think of a vector, right, we're going to think about a directed line segment. All right, and we're going to draw an example right here. All right, maybe we'll draw the directed line segment that joins this point to this point right here. So it's not just a segment, it's a directed segment, right? So let's draw the segment and then show that my initial point, all right, so this right here, I guess this has coordinates -4, -2, right? This is my initial point. And then I go to my terminal point, which is -1, +2. All right, so this is your terminal point. And it does matter which is which, otherwise the direction would be meaningless. So this is a directed line segment. And this is an example of a vector. All right, let's draw another directed line segment. Let's go from the origin. All right, so that's going to be at 0, 0 to, let's do the point 3, 4. Okay, so that directed line segment looks like this. All right, yet another directed line segment could be, I don't know, from this point over here to -1 to this point right here, which would be 5, +3. And when we put the arrows on, right, identifying which point is your initial point and which point is your terminal point, it becomes maybe clear that all three of these directed line segments are equivalent. All right, because they have the same magnitude, meaning the same length, and they are in the same direction. I'm sure you could calculate the length of each of those segments, and we will, all right, to show that they have equivalent length. And you could perhaps calculate the slope of each of those lines to show that they are in the same direction. But so all three of these are equivalent because they have the same length and direction. All right, if I had taken one of these and drawn the arrow the other way, right? Suppose that, instead of my initial point being at 2, -1 on the red line, suppose that were my terminal point. Now this vector is not equivalent to the others. It is the same length, but it is not the same direction. All right, so when we talk about a vector, we're actually talking about not just one directed line segments, but an entire set of directed line segments that have the same length and direction. All right, so all of these three are really just one vector, because we could move them around the coordinate plane and just reposition them, but ultimately they're the same thing. They're going the same distance in the same direction. So officially, for a vector, we're going to say a set of directed line segments that have the same magnitude and direction. Okay, so we'll say a set of directed line segments that have the same magnitude and direction. And so now, speaking of magnitude, you probably have an idea of how to calculate this, and so that's exactly what we're going to do. All right, we're going to move over to this other grid right here, and we're going to draw, some arbitrary vector. I don't know, we'll say that, you know what, let's mix it up a little bit. Let's have my initial point be over here, and let's connect like this. All right, and let's calculate its magnitude. All right, so this initial point has coordinates 3, 1, and the terminal point has coordinates -4, -3. Hopefully you're already getting an idea of how we calculate the magnitude, right? It's just the distance formula, right? So the magnitude is going to be, right, if you remember your distance formula, right, and I'm going to write it the way we typically show it, and then we'll slap some new sort of vector labels on it, right? That's going to be, right, your x2 minus x1 squared plus y2 minus y1 squared. So let's apply that here. Okay, so x2 minus x1, so we'll say 3 minus a -4, so 3 plus 4 squared, plus 1 minus a -3 would be plus 3 squared. So that gets us to 7 squared plus 4 squared, right? Which then gets us to 49 plus 16, which becomes, what is that, 65, the square root of 65? And you could go to the calculator and take that out to a decimal approximation. All right, and so when we talk about vectors now, all right, well, first you should probably know how we label a vector. So we're just going to call this vector v, okay? And now you'll either see a vector denoted in bold. That's going to be hard for me to do. So usually when we're handwriting a vector, we put this little arrow on it, okay? So that's typically what you'll see. You'll either see a letter with an arrow over it, or you'll see it bolded, okay? And so let's say that we had our initial point had coordinates p1, p2, all right, and we'll call this our initial point P, and this will be our terminal point Q, right, and it'll have coordinates Q1, Q2. All right, now we can, you know, put a different label on the magnitude of our vector, but ultimately it's just distance formula. All right, and so you see this right down here where it says the magnitude, also called the length, also called the norm of a vector, and I'm sure in a different course you'll get into why it's called the norm, but for now, just know that that means magnitude. And so there's our vector v, right, with the arrow on top, and let's say it has an initial point, right, p1, p2, and a terminal point q1, q2 is given by, and we're going to write down that exact formula, okay? But we're just going to substitute in our variables for our x1, x2, etc. Okay, so we'll have, all right, q1 minus p1 squared plus q2 minus p2 squared. And we denote the magnitude of a vector using this notation. So we write our vector v, and if we're talking about magnitude, we do double absolute value brackets. 1, 2, 1, 2. And that means the magnitude or length of v. Okay, next page. So as we mentioned on the previous page, all of those directed line segments that we drew were equivalent. They had the same length and they were in the same direction, so ultimately they all did the same thing. All right, that's why we only need one vector to represent them. All right, and often we choose the one that is in what we call standard position. All right, so standard position means that the initial point is at the origin. Okay, so let's write that down. So a vector is in standard position if the initial point is at the origin. So on the previous page, only one of the vectors was in standard position. It was the one that started at the origin and ended at the point 3, 4. So this one is in standard position. A vector that, you know, starts here and ends at the origin is not in standard position because, again, it has to be the initial point that's on the origin. All right, and what's nice about having vectors given in standard position is that you only need one set of coordinates to identify it, right? Because you know that the starting point is 0, 0. So instead of saying, okay, I've got a vector v, and that vector takes me from 0, 0 to the point 3, 4, instead of doing that, we can just say that vector v is given by 3, 4. And we put that in those arrow brackets. All right, that is what we call component form, all right, of a vector, meaning you just need to give the terminal point, all right? But we use those arrow brackets so that we don't confuse it with an ordered pair, so that we know it's actually a vector quantity. So component form just means that we'll say if our initial point is at the origin, or if our vector is in standard position, so we'll say for a vector v in standard position, and a terminal point at whatever, okay, in standard position, and a terminal point at, we'll say, v1, v2, it's sufficient to just identify the terminal point. All right, so we'll say component form is, and then those arrow brackets, v1, comma v2. Notice, those v's do not have the arrow on top because they're not vectors. They're just numbers, right? They just really identify where the vector ends. And v1 and v2, these are called the components of the vector. So in example 1, they ask us to find the component form and length of the vector from the ordered pair 3, -2 to -1, 3. All right, well, let's plot that, and then we'll sort of be able to generalize from there. So here's the ordered pair 3, -2. That's our initial point. And then -1, 3 is our terminal point. And let's show that it's a vector, so we'll connect them and we'll indicate the direction. All right, and if we want to put it into component form, we want to get this thing into standard position, meaning that we need to move the initial point to the origin. Okay, so that means that this initial point needs to move over 3 and up 2, and then it will be at the origin. But if we're going to do that to the initial point, we should do that to the terminal point as well. So we'll need to move it over 3 and up 2. And then there's our terminal point, and here's our new vector. All right, so now let's find the new coordinates of our terminal point. The initial point is easy. We know that's 0, 0 because we put it in standard position. So these new coordinates would be, what is that, -4, +5? Yep. Okay, so now how could we get that from looking at these ordered pairs, right, without having to draw it out every time? Well, you might realize it's just the difference between the two, right? So for example, if we start at 3, -2 and end at -1, 3, right, we can do, to get the component form, all right, we can just do the difference in the x's and then the difference in the y's. For example, right, so terminal x minus initial x, and then terminal y minus initial y. And then when you simplify that, you'll get -4, +5. And that is the component form of the vector that joins those 2 points, and it's just sufficient to give the -4 and the +5 because we assume that the terminal point is at the origin. And if you ever see a vector given in these arrow brackets, you have to assume that the initial point is at the origin, unless you're told otherwise. And now, finding the length should be easy. That's just going to be distance formula. But it's even easier now that we're in component form, because when we do distance formula, right, well, let's write it all out and we'll see exactly why it's easier. All right, so let's do our distance formula. All right, and so we'll say the magnitude of we'll just call this vector v. It hadn't been named. All right, and so we'll say, all right, difference in my y coordinates, right? So I'll use the 5 minus 0. You could obviously do this with the original coordinates, but I want to show you something with this. All right, so that gives us the square root of 5 squared plus 4 squared, right? Which then, when we simplify it, right, we're going to get the square root of 25 plus 16, which gives us the square root of 41, and that's about all you can do with it. But what's nice about having a vector in component form is that your distance formula to calculate the magnitude of your vector gets very easy, right? You can just throw the 5 and the negative 4 right in because you know that your initial point was 0 and it's not going to make an impact anyway. So if you want to, on the previous page, to your definition of magnitude, add, right, that if v is in component form, you can just calculate its magnitude like this, v1 squared plus v2 squared, provided that v1 and v2 are the components of v, right? But that makes it pretty nice and easy. All right, example 2, I am going to let you do on your own, but I will give you the answer so that you can check. If you put this into component form properly, you will get 5, negative 12. And then if you correctly calculate the magnitude, all right, you should get 13. All right, so try that on your own, give it a check. All right, and when you've done that, you can then go to the next page. So the great thing about vectors is that all of the operations that we'll do with them work exactly the way you would hope that they work. All right, for example, if you want to add two vectors together, two vectors u and v, you just add their individual components together, right? So for example, a vector u plus a vector v, right, and of course we're in component form here, will just be, you'll add u1 to v1, and you will add u2 to v2. And then if you have some scalar multiple times a vector, right, that's really like some scalar multiple times this component form, and you basically just get to distribute that right in. So that's the same thing as c times v1, c times v2. Everything pretty much works the way you would want it to in vector land. Okay, so if you're given a vector, right, and now this vector, we'll start with v, is in component form, meaning its initial point is at the origin and its terminal point is at negative 2, 5, right, it would be very easy to calculate the length of that vector. So if we now want to take half of that vector, well, you just need to decrease everything by half, right? So 1/2 of vector v will be 1/2 of negative 2, 5, so that will be negative 1 and then 2.5. It's as easy as that. Now if we want to do vector w minus vector v, we're just going to subtract individual components. So we'll say the first component of w minus the first component of v, and then the second component of w minus the second component of v. And that gets us to positive 5, negative 1. And so last but not least, for 2 times vector w plus vector v, right, you'll double vector w. So we'll just write it all out so that we can see it, right? So you need to double everything, and then you need to add v to it. So that will get us to the vector 6, 8, and then we'll add to it negative 2, 5. And again, we're just adding like component with like component. So 6 plus a negative 2 gets us a positive 4, and 8 plus 5 brings us to 13. Nice and easy, right? And so now down here, I think it's just worth going over what happens to the magnitude of a vector if you multiply it by a scalar, right? So if you have some scalar times a vector v, what happens to the magnitude of that vector? And it's pretty easy to figure out because we know how to calculate magnitude. All right, so again, let's assume that vector v has components v1 and v2, well then, if we add a scalar in front, we're just going to get c times v1, c times v2. So now let's go ahead and get the magnitude of c times our vector v. All right, and we're in component form, so we can simply just take the components and square them, right, since the initial point is at the origin. So we can say c v1 squared plus c v2 squared. And if we actually work this out, you're going to get c squared v1 squared plus c squared v2 squared. And if we continue up here, we can factor out the c squared. And so now you'll just have v1 squared plus v2 squared. And we can use some fun little properties of radicals here, right? Instead of taking the radical of the product, take the product of the radicals. And then the square root of c squared is c. And so you can see what we actually have is that the magnitude of our vector, if we throw a scalar in there, is just c times the magnitude of v. Not particularly earth-shattering, but it's kind of nice. It's just saying that if you scale each component of the vector by a factor of c, the magnitude also scales by a factor of c. Good to know. All right, next page. And so now, this brings us to a topic that we're actually going to use a lot in the next few coming sections, the idea of a unit vector. And a unit vector is exactly what it sounds like. It's a vector that's a single unit. In other words, it's a vector that has a magnitude of 1. So let's write that down. A vector with magnitude 1. And eventually you'll see why this would ever be helpful, why we would want a vector with a magnitude 1, right? But for now, we'll just introduce you to the idea. All right, so a unit vector is any vector that has a magnitude of 1. All right, and so ultimately what we're going to want to do occasionally is take a vector and scale it down so that it has the same direction but a magnitude of 1. So let's suppose that we found a vector that had a magnitude of 5. And I'm like, well, I want that same vector in the same direction, but I only want it to have length 1. What would you do to get that vector from a length of 5 down to a length of 1? Well, you could probably come up with a few options, and if we were in class, we would discuss, right? But ultimately, somebody would eventually say, oh, just divide it by 5. And that's exactly what you do. If your vector has a magnitude of 5 and you want it to have a magnitude of 1, you divide by 5. In other words, you divide by its magnitude. So, if you have a vector, v, with components v1 and v2, you can find a unit vector, right, a vector of length 1 that will be in the same direction as v by taking v and dividing it by its magnitude, so that if the magnitude of v is 5, we divide by 5, and now our magnitude is 1, right? So you can also write that as 1 over the magnitude of v, and then times its individual components, however you like to think about it. All right, so let's try that for example 4. It says find the unit vector for the vector given by -2, 5 in component form and verify that it has a length of 1. All right, so first we need to figure out what's its current magnitude, right? Because we need to know how much we need to scale it down by. All right, so the magnitude of vector v is going to be -2 squared plus 5 squared, since we can assume that our initial point is at the origin, which becomes 4 plus 25, which becomes root 29. Okay, so we need to scale this thing down by root 29, right? Its magnitude is root 29. I want it to have magnitude 1, so I need to divide the whole vector by root 29. In other words, I need to do v over root 29, which looks like this. 1 over root 29, all right, times negative 2, 5, which we'll really want to write as negative 2 over root 29, and then 5 over root 29. And I'm going to leave it as an exercise for you to now take this new vector, this unit vector, and verify that its magnitude is 1, which means that you can just do this distance formula again, but with your new, right, with your new components here, all right? Verify that this vector has a length of 1, that it is actually a unit vector. All right, so you can pause the video, work on that, convince yourself that this whole thing works out. Now that you've proven that that vector has a length of 1, we're going to move on, all right, to something that we call standard unit vectors, all right? And in general, what we mean by a standard unit vector is that its direction has just one component, all right? All of the vectors that we've drawn so far, they're at a slope, right? They're sort of at an angle. So they have some horizontal movement and some vertical movement. When we consider unit vectors, all right, that are standard, we really mean vectors that, again, have a magnitude of 1, but their direction just involves one direction. All right, so for example, the unit vector 1, 0. You could easily show that this has a magnitude of 1, right? Just doing what we always do to find magnitude. All right, but now let me show you what I mean about the direction. I'm just going to draw a little mini coordinate plane right here. Okay. And so my unit vector 1, 0 would be like this, right? It would bring me to the point 1, 0. And notice its motion is strictly in the horizontal direction. The other unit vector is, as you might have guessed, 0, 1. Its motion is strictly vertical, right, up and down, all right, just in one direction, but also has a magnitude of 1. All right, now, these unit vectors come up so much, we give them special names, all right? We say that the vector 1, 0, we call it I, and you'll see this a number of ways. You'll see it as I with, the little arrow over it. You'll sometimes see it as what we call I hat. It's got like a little arrow on top, but ultimately that just denotes the unit vector 1, 0. Similarly, J, sometimes with an arrow over it, sometimes bolded, sometimes as J hat. That's the unit vector 0, 1. Okay, they mean the exact same thing. All right, so let's go to example 5, and if you can do example 5, you're pretty squared away on your unit vector business. All right, so that it says, suppose that U is the vector joining the point 2, -5 to -1, 3, and then V is 2I minus J, right? So now I and J refer to those special unit vectors that we just discussed. Write the vector W given by 2U minus 3V in terms of the standard unit vectors. So that means I and J. So I would say that our first order of business is to get this into standard position, because if you notice, the standard unit vectors are in component form. They use those little arrows. So we need to get vector U into standard position. So let's say that U equals, and then again, remember, we just take the difference of the individual components. So we'll say -1 minus 2, right? And then 3 minus -5. And that gets us -3 and +8. Now, let's try writing this using I and J instead of -3 and 8 in component form. All right, so now notice what we can do here. We can say that -3 and 8, that's the same thing as saying -3 times the vector 1, 0, right? If I distribute that -3 in, I get a -3 for the first component and nothing for the second, and then 8 times the vector 0, 1. Okay, and let's just verify that this works. Okay, let's just convince ourselves. So let's distribute this in. And we get -3, 0, right? When we just multiply in our scalar, plus when we distribute in the 8, we'll get 0, 8. And now, when we add these two together, we know that we just add their individual components, so that would be -3 plus 0, and then 0 plus 8, which would give us -3, 8. Okay, so we're actually now going to pick up from this point right here. All right, we've convinced ourselves that we can make this step. All right, so now we have -3 times the vector 1, 0, oh. That's just I. So from here, I'm just going to scoot down here. Let's write this as -3 I. I like to use the hats. All right, and then we have plus 8 times the vector 0, 1. Oh, that's just j. So we'll write j hat. All right, so that's our vector u written in terms of I and j. And we already have vector v written in terms of I and j, which is nice. So now, if we go to find w, all right, writing it in terms of I and j makes very quick work of it, right? So let's just remind ourselves, w is equal to 2 times vector u minus 3 times vector v, which is going to be 2 times, u is -3 I plus 8j, and then minus 3 times vector v, which is 2I minus j. Whoop. And then from there, we can just simplify, right? We can just distribute the 2 to each of these components, right? So we'll have -6I plus 16j minus 6I plus 3j, and then you can combine like terms and get -12I, and then what's that, plus 18j? And so this makes very quick work of adding vectors when you're able to express them in terms of the standard unit vectors I and j, because then you just add sort of like terms in a way. Add up all your I components, add up all your j components, and you're good to go. All right, so hopefully this has been a nice little introduction to the world of vectors, and we'll continue with some more sophisticated applications in the next section. Bye-bye.